So in this lecture we are going to discuss about exterior derivatives. That means we want to take derivatives over forms on a manifold. So in calculus what we do is that we take some function and then we can define a derivative that will measure the rate of change of that function, right? But when we do calculus on manifolds, we have seen that the objects that we concern ourselves with is forms, whether it's a one form or a two form or a three form, and the goal of this exterior derivative will be to measure, in some sense it will measure how these forms change. So the idea is to define a similar analog of derivative for forms. This is our goal, and we'll try to see a little bit of a geometrical picture. Again, this picture is not entirely accurate, but it gives you some idea what this exterior derivative does. Okay, so first things first, let us define a one form. So let's say we have a one form like this, a one form that is written as alpha, which is defined via the following. This is a summation symbol, this, where dxi is a one form and this fi which can be a function of our coordinates is a scalar. That means it's a zero form, right? Now the exterior derivative which is written as d of alpha in this case, because it will try to change it will try to measure the rate of change of this alpha, will be defined as follows. Let's say this is again this index I summation over I as d of fi wedged with d of xi, like this. And since you know about that how to take the total derivative of a zero form, that means a scalar function or a vector function, you already know how to evaluate this d of fi. So this will just be the partial of, let's say, xij. Don't mind these indices, they are just here to keep tracks of stuff, of dxj dxi, and this summation will now go from I to I of j. This is how an exterior derivative is defined. But how do we know that this should be the way and this is the way it measures some changes? So that will be a long discussion, and we'll try to provide a very short geometrical picture in this lecture. So as you can see from here that we are explicitly introducing the coordinates. However, you can write the exterior derivative in such a way that it doesn't depend on the coordinates itself. So this is the coordinate dependent version. The end result would be the same. We should emphasize that as well, that whatever you do, the end result will be same, but there are just two ways of writing the exterior derivative. So this is the form where the coordinates appear explicitly. So coordinates appear explicitly. It's also known as the local formula, and this is the coordinate free version. And this is written as d of alpha, which acts on two vector fields, which can be in general constant or non-constant. These are just two vector fields, and this is written as v, which is acting on this alpha w minus w of alpha of v minus alpha acting on the commutator of v and w, like this. And we already know how a form acts on a vector field, right? And now we want to discuss these things. So the motivation behind this exterior derivative is that it should take an n form and it will return a n plus 1 form. Motivation behind this definition is that it will take a n form and return a n plus 1 form. So that means that d or exterior derivative is such an operator that is defined like this, where M is the manifold and this is the space of the forms, the space of the n forms, n plus 1 M, like this. Why? Because if you look at the ordinary derivatives in calculus, your function, let's say f of x, was a 0 form. When you take the derivative of this function, it gives you a 1 form, like this, right? This is a 1 form. So this is where the motivation comes from. This is one way to look at it. And obviously you can, if you are dealing with multivariable, you just can put a summation symbol over here and you are good to go. So now let's say you have a n form and you want to apply an exterior derivative on that n form. So just like this definition over here, let's say our n form is something like this and we want to apply the exterior derivative operator. This n form is written as alpha I j k dot 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 dot. Let's say some x, or we can be a bit more careful and write it as I1, I2, I3 dot 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 I of n, like this. And this alpha again is a coefficient that is coming with some indexes, and there will be forms written as dx I1, dx I2. Obviously there will be a wedge product, otherwise it won't be considered as a n form. 3 dot 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 wedged with dx I of n. And once you apply this exterior derivative onto this thing, what it does is that it will take the partial derivatives of the zeroth form. That means I1 alpha, I2 alpha, sorry, not alpha, sorry about that, I1, I2, I3, I of n, partial derivative of xij, like this. Again, these are just indexes. There is no chance that this is a two variable thing, it's a single variable thing, but this index will actually give you what is this ij component of the coordinate that you are considering. Now it will put another dx and this will come as index of j in front of this whole thing, and then you will have the thing that you started with initially. So this is a way to compute it. So let's try to see an example right now. Let's say you have two functions, let's say f of xy and g of xy. And if you notice a little bit carefully, what it does is that it's just a mapping. That means from xy there is a mapping to this f and there is a mapping to this g, right? So let's consider a very simple thing. That simple thing is that what is df wedged with dg, which we learned in our previous lecture is a projection of the area, right? We want to compute this quantity. So let's say this is your xy plane and this is a FG plane. So this is F and this is G. So you have some infinitesimal area over here and you want to see how this area looks when you go to this FG plane. And let's say it looks something like this and we want to see how they're related. So that's why we want to carry out this computation. So what is d of f? Again, this is easy. Since this is a two variable functions and we are computing a two form, this is a two form thing. Df is nothing but, by the definition, that this is a partial with respect to x dx and this is just dy like this. Okay, now you can consider this dg as this similar thing. And then you can easily compute the wedge product. So if you compute the wedge product, how you will do it? This is just df dx plus df dy wedged with del g del x plus del g del y dy. So note something, that even though we are considering a wedge product, you can see from the fact that these f's, these are f and g, these are zero forms. So we are taking one forms using this exterior derivative over here, which you already know as a total derivative thing, right? So if you compute it, this is nothing but df dx dg dx. And now what I'm going to do is that I'm going to show a new notation which will just make our life a little bit easier. Is that instead of writing this del f del x like this, we can write it as del x f. This index will indicate with respect to which variable we are taking the derivative or the partial derivative. So if I write in that way, this becomes very simple to write. Dx f dx g, and there will be dx wedged with dx. Similarly, we have dx f yg dx wedged with dy. Then you have this y f xg dy wedged with dx, and finally you have y f yg dy wedged with dy. And you can already understand that this will be 0 and this will be 0, so as a result both of these terms will go away. And now what we can do is that, we can use this anti-symmetry property of the wedge product to our advantage to make things a little bit more simpler. So let's do that. So this is dfx dxg, sorry, not this one, it should be dy f dyg. Let's keep this dx wedged with dy. However, we want to switch dy and dx over here so that we can factor out these two form, and we want to put these coefficients in a single bracket thing so that it becomes a little bit simplified. And there will be a minus n because dx wedged with dy is equals to just minus dy wedged with dx, like this. Okay, and if you do that, this is just df dyg dx wedged with dy. Now finally you can write this whole thing in its full glory, minus y g. Oops, it shouldn't be y, it should be x, right? Yeah, this should be x. And you have this dx wedged with dy. So this in turn can be also written as df dx, dg dy, then df dy, and dg dx, and dx wedged with dy. So finally what you have is df wedged with dg is this. So this is the so-called area in FG plane. This can be thought of as the area in the xy plane, and this is our scaling factor, which is also known as the Jacobian or the Jacobian, whatever you want to call it, or some people call it the determinant of the Jacobian matrix. So in multivariable calculus, these things are derived in a very tedious way, but once you adapt to this notation of calculus on manifolds and differential forms, you can see that this arises very naturally. So this is one example, and let's consider another example. Let's say we have some function f of x, y, and z as x cube, then let's say y square and z to the power 4, like this. And we want to compute what is this guy when you take a form of it. That means this is already a 0 form, right? So you can obviously make a 1 form out of it by using this df. But what we want to see is that how to do these calculations when you are actually going to compute a quantity like this, d of f, right? That's what we want to consider, because that was the very motivation for introducing this exterior derivative, so that we can take derivatives of forms, right? So df is pretty easy. This is again dfx dx dy f dy z f dz, and this is just 3x square y square z to the power 4 dx, and then you have this x cube, then is a 2yz4 dy, and this is just 4x cube y square z cube dz, something like this. All right, and let's say this is just alpha, which is equals to some one form, and we want to compute what is d of alpha. So how do you compute d of alpha? Well, use the definition that introduced above, and you have to first take partial derivatives of these guys and then wedge this with this one forms like this. Okay, so for now let me just write it like this, 3, because if you recall that if you had a 0 form, this is how you would write the 1 form, right? So using this, we can write it as 3x squared z to the power 4, and we now put a wedge, and then similarly 2x cubed y z to the power 4 dy is a wedge, and then we have this d 4x cubed y squared z cube wedged with a z. Now we have to evaluate this part, and this part, and there are wedges everywhere. So one thing you will notice is that there is already a dx over here. So if I want to compute this part, let's denote it with this red color. You know how to do it already. Since this is a function which is a zero form, you just write d of 3x square y square z to the power 4 as following. This is nothing but, first take the partial derivative with respect to x and leave the other terms alone, and this will give you 3, and there will be a 2 multiplier, so it will be 6x y square z to the power 4. There will be a dx plus, then there will be a partial derivative with respect to y, and then there will be a partial derivative with respect to z. So what you are actually doing, you are just calculating the total differential. And if we write down the later terms, we will have something like this: 6x square y z to the power 4 d of y, and finally 12x square y square z cube dz, right? And there is a wedge like this, and you already know that dx wedged with dx would give you a 0, so this term will contribute nothing, and these two terms will contribute some non-zero stuff. So this expression will yield the following result. This will be 6x square y z to the power 4 dy wedged with dx, and then you have this 12x square y square z cube dz wedged with dx, like this. Now for this term, d of 2x cube y z to the power 4 wedged with dy, what it should give you? Well, again compute this guy, and if you try to compute it, it will give you something like this: 6x square y z to the power 4, there will be a dx wedged with dy, then there will be a y term. That means when you do the partial derivative with respect to y, there will be a dy, and that will get wedged with this dy, and that's why I'm not writing that term. It will be 0, and the last non-zero term would be just 8x cube y z cube dz wedged with dy, and the final term will be d of 4x cube y square z cube, right? 4x cube y square z cube wedged with dz. So similarly, this term will give you 12x square y square z cube dx wedged with dz. Then you'll have 8x cube y z cube dy wedged with dz, like this. And let's call it 1, 2 and 3. Now according to this line, this d alpha, 1 plus 2 plus 3 will give me the d alpha thing, and what we can see over here is that we have this dx wedged with dy, dy wedged with dx. So let's try to collect all the terms and simplify directly. So first we want to write the terms with dx wedged with dy. So let's write dx wedged with dy, and we want to collect the coefficients over here. So this is one of the coefficients of dx dy. This is one. Then there is another one over here, and then there is none. So if you write the wedge product as dx dy, then you have to switch the order over here, which will give you a minus sign. So if you see carefully that these two terms are equal to each other, and when you switch this, you are getting a minus sign. So in total you are actually getting a 0. 6x square yz minus 6x square yz, and this is what? This is 0. Does this happen for the other terms as well? Well, let's see. What about dy dz? And this is dz dy, and you can see there are no other wedge product that involves y and z only. And again, these two terms are similar. if you switch this order over here or another order over here, one of the coefficients will pick up a minus sign, and these two terms will actually cancel each other out. Similarly for these two terms as well. So in total what you are getting is a 0. So what is happening over here? We are calculating this d of f, right? And we are getting a 0. So this is a very famous property that exterior derivatives show, is that for any n form d of that form, so let's call this form as, let's say, gamma. d of gamma will always be 0, always. And this is sometimes also written as d square operator. It takes something and it puts it 0, and it has a famous interpretation that the boundary of a boundary is 0. This might not make sense right now, but we'll get to that later. And this will be more clear when we do integration with forms. Then we will realize why these are called boundary of a boundary terms. Alright, so now since we have seen some examples, we now want to write down a few algebraic properties of these exterior derivatives. Algebraic properties of exterior derivatives. And after this I'll try to show you a very simple geometrical picture, and then we'll be done with discussing this exterior derivative stuff. So the algebraic properties are the following. So let's say alpha and beta both are n forms, okay, and let's say omega is another m form. The following properties hold. If this is true, then the following properties hold, is that d of alpha plus beta would be equals to d of alpha plus d of beta. 2 is that d of alpha wedged with omega will be d of alpha wedged with omega plus minus 1 to the power n alpha wedged with d omega. And the third one is the boundary of a boundary thing. That means dd of alpha will always be equals to 0. In fact, you can think these three things as axioms as well. If you take these axioms, then these axioms will lead you down to this definition of a exterior product, where you have this d that takes some n form and returns a n plus 1 form, like this. It can be also, this might seem a bit circular, but that's how things are. And now we want to show you a very simple geometrical picture of this exterior derivatives. So if you recall that we said that there is a coordinate free way, that means a coordinate independent way of writing the differential forms, and that was written as follows, is that, if you recall that we wrote it a bit while ago, so let me get back to that. This one, this is the coordinate free way of writing a differential form, exterior derivative. So what does it mean? What it means is that when you have a manifold and you have some differential form alpha, and you have two vectors given by this v and w, you want to measure the change in alpha. So what you do is that you introduce two vectors, and let's say this is the manifold and this is the first case, and let's say this is the manifold again, and this will denote the second case. So in the first case, what happens is that you can take those alphas and you want to get a weighted sum along the v direction, or so to say, you want to see what happens to this alpha when you take this v vector and make a weighted sum of it. Obviously v can be a constant or a non-constant vector, and then what you do is that you move in the w direction and see how things change, and after that you do the converse. That means now you take your alphas and make a weighted sum with the w's, sorry, this should be a v, w's, and then you want to move in the v direction and see how the form changes, because there is no direct way of measuring a change in the form. So what you do, you associate some vector fields with the form and then you try to measure the changes. So if this gives you tangent plane like this on the tangent plane, sorry, on the manifold, and this gives you another tangent plane like this, from a geometric point of view, what you are doing is that you are actually going towards this way first and then this way. So if this is your v, alpha of v in the direction of w, then the other, oops, like this would be, say, alpha of w in the direction of v, and you want to let's say this is your test vector and you are going towards this way in one, this is one way and this is another way, and you want to finally measure the difference. So this is one way to see this geometrical picture of the exterior derivative, but it will become more clear when we see the integration of differential forms, and we will also see that this idea of this exterior derivative is extremely powerful, because you can write all of vector calculus, all of multivariable calculus within a few lines. Theorems like curl, divergence, Stokes phenomena and Stokes theorem and stuff, all of this can be written in a very compact way and they can be interpreted as such with this exterior derivatives. So this will be it for today, and I'll see you guys on the next lecture. Thank you.